All right, welcome to AP Chemistry. We're looking at Unit 1.6, and our essential prompt is to use Coulomb's law to explain how nuclear charge can be used to determine the relative attraction that valence electrons have for the nucleus. And in answering this, I just want to make sure we look at our AP learning objective, and we're explaining, yes, that is explaining the relationship between the photoelectron spectrum of an atom or the photoelectron spectrum of an ion and the ground state electron configuration. So we see photoelectron spectrum and the ground state electron configuration. And then we also see a relationship between the photoelectron spectrum and interactions between electrons and the nucleus. And if we look at our essential knowledge, the energies of the electrons in a given shell can be measured experimentally with PES. The position of each peak in the PES spectrum is related to the energy required to do what? Remove an electron from the corresponding subshell, and the relative height of each peak is ideally proportional to the number of electrons in that subshell. And I think we're going to learn all of that essential knowledge today. You're going to see that everything that's said in essential knowledge is what we're bringing out here, and it matches our learning objective quite tightly. So the first part says we should write the electron configuration from a photoelectron spectrum. And then let's look and see. It says, what is binding energy? I put here binding energy, and it even says this in the essential knowledge, but the binding energy refers to the energy needed to remove an electron from an atom or molecule using these high energy photons. And so we can analyze the amount of energy needed for this, and we get some insights of some chemical composition of a substance. All right, so that's our binding energy. Now, binding energy is strongly related to Coulomb's law, and when we talk about Coulomb's law, this F is either referring to the force of attraction or the force of repulsion, and you can think of if we have a higher force of attraction, that the binding energy is going to be higher, because if you have an electron that is more attracted to the nucleus, then it's going to take more energy to remove it. If you have an electron that is less attracted to the nucleus, then it's going to take less energy to remove it. Do you see that? So this force of attraction is that we're going to just look at it in terms of attraction, because we're looking at protons and electrons, the protons in the nucleus, attraction with the electrons outside of the nucleus, right? And so we have oppositely charged particles, and so we're talking about attraction. And so these things are related. Q1 and Q2 are charged particles, our protons and our electrons, where R is the distance between those two particles, right? And we've already kind of looked at this before. The further apart substances are, the less attraction there is, right? And the closer they are, there's going to be more attraction. We thought about the magnet example from the other day. So when we talk about binding energy and thinking about Coulomb's law and how that force of attraction is related to binding energy is very, very helpful. Okay, so we should be able to write electron configuration. What we're going to do here is we're going to actually just draw a PES, the photoelectron spectrum, and we're going to do this for a couple of these. I kind of changed my mind since I wrote this morning. So we're going to leave out magnesium, and we're just going to use sodium and the sodium ion, and then we're going to use chlorine and the chloride ion. All right, so that's what we're going to do. So we're going to start off with sodium, and then if we're writing our PES, the first thing we need is the electron configuration. Did I tell you that in our learning objective, we need to know the relationship between the PES of an atom, in this case sodium, and what? Its electron configuration. That's what we're doing here. This is why we're writing electron configuration. So what energy level is sodium in? Energy level what? That's right, 3. All right, so it's 3s. You can talk. All right, so 3s, and it's 3s1. So we fill everything in up to that, 1s2, 2s2, 2p6, and we're at 3s1. Now, how can we know whether we have the right configuration? We can do what? We can count. And if this is a neutral charged atom, sodium has 11 protons. This should have 11 electrons. You see that? And there we go. Now, we're going to draw our photoelectron spectrum on this graph. And so what we're going to notice on this graph is two very important things. One is that larger values are where? On the left. That's weird, right? And smaller values are over here, right? So as you go left to right, the values become smaller. Now that you don't see that on every PES there is. If you Google PES, you might not see that. But at least for your AP testing, it's going to look like this. All right, this is not abnormal. It's not just AP that does it, but when they test you, you're looking for the larger values, or those that have the higher binding energy are going to be on the left, and the smaller values for binding energy are going to be on the right. Notice the x-axis is also dealing with what? Binding energy. That's a big deal. Don't you think it's important to pay attention to the labels of your graph? Yeah, that's a big deal. So moving left to right, it's referring to binding energy. And if we're referring to, so here's binding energy. And if we're referring to our y-axis, we see that it's dealing with what? Relative number of electrons, not the number of electrons, but the relative number of electrons. And sometimes you will see this word, intensity. So it has to do with the intensity of the peak. And this intensity is referring to the relative number of electrons, not the number of electrons, but the relative number. And why is that important? Because when we say relative, that means we are relating one thing to another. Do you see that? That's what the word relative comes in. We are relating. So we're going to have to relate one peak to another peak in order to determine the number of electrons in other peaks. All right. Now, how can we do that? Well, we do it by starting with. Well, before we go any further, I want to do this. I want to draw a Bohr model of sodium. So here is sodium, the nucleus, and here is energy level 1, and here is energy level 2, and then here is energy level 3. And I wanted to point these things out because let's draw some electrons here. There's 2 in energy level 1. We look at our electron configuration. How many electrons are in energy level 2? 8. 2 in the S and 6 in the P, right? So there's a total of 8. 2, 4, 6, 8. And then in the third, there's how many? 1. Now, this is taking us, what I'm about to say is taking us to this part 2 of that learning objective, the interactions between the electrons and the nucleus. You see that? And so what we're going to look at is this idea of Coulomb's law, right here. So if we look at energy level 1, we notice that those electrons are closer to the nucleus. So what does that tell you about the force of attraction of these energy level 1 electrons relative to the electron in energy level 3? Yeah, they're greater. You see that? Why? Because they're closer. Look where R is. So if R is a small value, what happens to F? It becomes bigger, right? So the force of attraction is greater. And if the force of attraction is greater, then it's going to take more energy to remove the electron, which is referring to what? Binding energy. And where do we find binding energy? On the x-axis. Do you see that? And so we look at, and we don't have data for this, so this whole spectra is just relative. We're just throwing some peaks here, and one peak relative to another. All right, because we don't. It's not like we have actual data. but this will help us read, right? So I want to say we have sodium in energy level 1. How many electrons are there? 2. And let me also ask this question. What sublevels exist in energy level 1? There's S, P, D, F available. Which one is the only one in energy level 1? S. And S holds how many electrons? 2. So this first peak on the left has the highest binding energy. Why? Because those electrons are what? Closer to the nucleus. Look at our model. Look at our Bohr model. Energy level 1, those electrons are clearly closer to what? The nucleus. That means the force of attraction is higher. That means the binding energy is higher. Now, I can assign whatever peak height I want when I'm drawing this, right? So I could say the peak height for 2 electrons is this high. Do you see that? Does it? I could say it is this high. It does not matter. Do you see that? That represents 2 electrons. And then other peak heights would be relative to that value. Do you see that? So if I then said I have 4 electrons, my peak height would have to be twice as high. Do you see that? Do you see that? So that's what that means. Now, I don't want to do that because I want to be able to draw this thing sometime today. So I'm going to erase this, and I'm just going to put this on. But you understand, they can be any height. It doesn't matter. It really does not matter. But we're going to put it as, just for simplicity, 2 lines represents 2 electrons. All right? Does that have to be that? No. So this is our 1s peak. Our 1s peak. How many electrons are there? 2. Why does it have the highest binding energy? Because it's those electrons are closest to the nucleus. Do you see that right there? That's answering this. The relationship between PES and the interactions between the electrons and the nucleus. Do you see that? What's causing that attraction to be greater? The distance is closer, right? There's a smaller distance. Now we can go to energy level 2. Now there are 2 sublevels in energy level 2. There's an S and a P. Do you see that? So we're going to draw a 2s peak. The S peak happens to be a little tight, more tightly bound than the P. All right. So what you'll do is you're going to draw a 2s peak. Now, how many electrons, according to our electron configuration, are in the 2s? How many are in the 2s? No, in the 2s. 2. All right. So what's our peak height? The same as the first one. Why? Because these are relative numbers, right? If this peak at 1s, if this peak here is 2, and we have 2 electrons in the 2s, well, it has to be the same height, right? You're relating one to the other. If we said that the first peak was up 4 lines, and that was 2 electrons, then the second peak would have been up 4 lines to represent also 2 electrons. Do you see that? It's all relative. So we're relating one to the other. So this is 2s. And how many electrons are there? 2. Then what's next? 2p. Now, how many electrons are in that 2p? 6. So what about my peak height here? What is the peak height going to look like? It's going to be how many lines? 6, because 2 was 2 lines. So 6 must be what? 6 lines, or it's 3 times greater than the 1s peak. Do you see that? So we're going to count those 1, 2, 3, 4, 5, 6, and then I can draw my peak. There it is. This is 2p, and there are 6 electrons. You see how it's 3 times the height. It's not that this height represents 6 electrons all by itself, right? It's that this is 3 times greater than the 1s. Do you see that? Which means there are 6 electrons there. The 1s always is going to have 2 unless you're dealing with hydrogen. All right? And then it's just 1 peak at 1s1. All right? But outside of that, there's going to be 2 electrons in that 1s peak. All right. And then we get to the last one, and it's energy level 3. You see that? Energy level 3. So where's that peak going to be relative to the others? It's going to be to the right. What about its peak height? It's going to be 1 or half of the 1s. You see that? So this would be, you see how that peak height is half of the 1s? Because it's representing how many electrons? 1. So there's 3s, 1 electron. You see that? Yeah. Not too hard. We just did exactly what that learning objective asked us to do. We related an atom, right, and its electron configuration to what? The photoelectron spectrum. Now, we did that for an atom. Did we do that for an ion? Did we do that for an ion? No. So what if we did that for an atom, for an ion? Here we have sodium, and let's say it's 1 plus. Sodium, we should know, is a metal. Metals tend to lose electrons to form cations, right? So if it's 1 plus, that means it's going to lose an electron, or it's going to become 1. It's going to have a noble gas configuration. It's not going to become a noble gas. 1s2, 2s2, 2p6. Or you could say, if you're using an abbreviated, that it is what? Neon, or has the electron configuration of neon. It is not neon. You know why it's not neon? Because it still has what? 11 protons. You see that? Look at your handy dandy periodic table. I suggest everyone look at it, especially you watching online. So we have the sodium ion. It has the same electron configuration as neon. Now, I'm going to draw our PES of neon right alongside of this. I'm not of neon, excuse me, of the sodium ion, just right alongside this. So what we should know about sodium ion is that it has 11 protons, but it has fewer electrons, right? So if we were going to show the PES for this, what are we going to see? What are we going to see? Is the attraction going to be greater or less than? Well, say again. Less than what? Here, let's do this. Let's do this. I'm gonna do this. I'm gonna say this is, I just removed the 3s. Do you see that? So let's say that I have sodium ion already written. Can we go with that? So this has 1s2, 2s2, 2p6. Now we're going to say that it's the sodium ion, right? Now let's just draw in neon. All right, we're going to draw we're going to draw in neon. Neon being what? 1s2, 2s2, 2p6. All right, I want to do this because I think this will make it a little more clear. So if we show the difference between the sodium ion and neon, both have the same electron configuration. This is why I want to do it this way. All right, so both of them have the same electron configuration. Now, is neon or sodium ion going to have, let's ask this, where's the 1s peak or the neon ion relative to what we see on the graph already, which represents the sodium ion? Where would it be, to the left or to the right? And so if we say to the left, we're saying that neon would have a greater binding energy or greater attraction. But if we look at our periodic table, we notice that neon has 10 protons, right? Whereas sodium ion has what? 11. Now you think about, now we're dealing with this area here, this numerator, right? So we have more protons and the same amount of electrons. So if we have more protons with the sodium ion, what does that mean? The force of attraction is going to be greater, and the binding energy for the sodium ion would be greater than the binding energy of neon. Do we see why? All right. Now, so what we would see is that neon actually would have a lower binding energy, all right, at the 1s peak. Where else is it going to have lower binding energy? At all other peaks as well. All right, so the same thing. So this might be the 2s, and this would be the 2p. Do you see that? Do we know why? Because there's more protons in that ion. Do you see that? Yeah. And that's for the cation. Do you see that? That's true when we have a cation. The neon. The neon. Yeah. So the purple is representing the sodium ion, and then the red or pink, whatever color it is representing the neon. Does that make sense? Okay, and so I just want to point out again, they both have the same electron configuration. Why does neon have peaks to the right or showing a lower binding energy at each peak? Because it has fewer protons. If we look at Coulomb's law, we're in the numerator, right? They both have 10 electrons, but whoa, sodium ion has 11 protons. That's causing the force of attraction for sodium ion to be greater than the force of attraction for neon. All right. We okay on that? Only mildly confused? It's great, but we did talk about an atom and an ion. You're gonna get some practice with that. All right, let's do another one real quick. I'm gonna erase this, and then we'll do another one real quick with chlorine. Maybe I won't make it so confusing this time. Wow. Okay. I would say names, but I don't do that. Okay, because then I'd have to re-record. Okay, so purple is going to represent. Let's go with a couple of these. Let's go with blue, representing chlorine. Chlorine. Electron configuration of chlorine is what? What's the final one? 3p what? Good answer. 3p5. So 1s2, 2s2, 2p6, 3s2, and then 3p5. Right? So if we draw our binding energy, we're going to show 2 electrons. Here's our 1s. Here's our 2s. Here's our 2p. 1, 2, 3, 4, 5, 6. Just make sure I get it way up there. Here's our 3s. Notice it's the same height, 2 electrons. And then 3p5. Where's that going to be? Boom. 1 less than the 6. Do you see that? All right. So maybe you don't see it. Maybe that helps out. So this is 2p, 3s, 3p, right? Can we tell the relative number of electrons? That's what they're going to ask you on your test. All right. They're going to ask you an easy question. How many electrons are in the valence shell? What's the valence shell? Okay, based on this, what's the outermost ring? Everything 3, 3s and 3p. Do you see that? So how many would it represent? No, 7. 2 plus 5. Yeah, you see? Don't answer too quick. Look. No, it's okay. This is why we go over it now, right? So we don't miss it later on. It's not a trick. It's not a trick. I won't call you out. Not right now. Later on I will. Okay, so not right now. So yeah, when I'm not recording. All right, so now let's ask this question. Chlorine. When it forms an ion, what charge does it form? Chlorine as an ion has 1 what? Minus. Remember, chlorine is a non-metal. Non-metals tend to do what? Gain electrons. So our electron configuration here would be 1s2, 2s2, 2p6, 3s2, and 3p6. You see that? Now, just so I don't confuse you thoroughly like I did last time, I'm going to erase this and just draw it again, even though it's pretty much the same thing. All right. So, but somehow you'll be less confused. All right. So we're going to have our 1s, and then we're going to have our 2s, and then we're going to have our 2p, 1, 2, 3, 4, 5, 6. Here we go. And then we're going to have the 3s, and then now 3p6. Notice they're the same height, right, as the 2p6, right? Why? Because the height represents what? The number of electrons, or the relative number of electrons. So now, there is that. Now, if we, what do we know about the chloride ion? The chloride ion has what configuration? It has that of argon, right? Is it argon? No. No, it's not argon. All right. So let's draw the peaks for argon right next to this. So here's now we're going to draw the electron configuration for argon, which happens to be 1s2, 2s2, 2p6, 3s2, 3p6. What is that? Oh my gosh, they're the same. Okay, but wait, are their peaks going to be identical? No, but this time the ion has fewer protons than the noble gas. Do you see that? That we're comparing it to, even though they have the same configuration, right? So what does that tell you about the peaks for argon? They're going to be where? They're going to be to the left, all right? So because we're just drawing relative stuff here, this would be maybe argon, right? So we show these to the left, and then we can say, wow, I know why argon has a higher binding energy at each peak, because it has what? More protons. Again, if we go back to Coulomb's law, we are at the Q's, right? We're saying R is even Stevens, but that was probably not a recording sound. Even Stevens, but the Q is a little bit higher for argon, right? Do we understand that? So when I say, did we talk about this? Are we showing a relationship between PES of an atom and an ion? We talked about them both, right? Did we relate that to the electron configuration? You doggone right we did. Did we relate that to interactions between the electrons in the nucleus? What do we mean by electrons in the nucleus? The force of attraction that occurs, right? How do we know about the relative force of attraction? We look at what? Coulomb's law. Higher force of attraction, higher binding energy. Lower force of attraction, lower binding energy. We looked at this PES. We notice higher binding energies are on what side of the x-axis? On which side? I'll give you a hint. This is left, and this is right. Yes, on the left-hand side. All right. I didn't know. I just learned today. All right, it's all good. Maybe that lunch is hitting you pretty hard. You guys like, I'm not sure. Taco Tuesday got me thinking all kinds of backwards. All right. All right, don't tell Cameron. All right, so ooh, I can't say the name. Don't tell the chef. All right, so there we go. All right, let's move on to the next part. These next parts, I'm really just trying to show you how this stuff is used. All right, so here's a question that you might be asked. Which of the following elements might this spectrum represent? So we have a peak over here on the left. Which electrons are those from? How would we describe those at 84? They are 1s. How many electrons are there? 2 electrons. Holy smokes, y'all are good. What about the peak at 4.7? That's 2s. How many electrons? 2 electrons. All right. And then the one at 2.0. 2p what? 2p6 representing, well, it's 2p representing 6 electrons, right? So our electron configuration is 1s2, 2s2, 2p6, which is representing what? Holy smokes, there's no way it's that easy, right? Did we just do that? No, we didn't. All right. Unbelievable. All right. Put me on 2 times speed because you got this. All right, moving on. Sound the same. I sound the same. All right, so I sound the same. Anyway, given the spectrum above, identify the element and its electron configuration. Can you identify the electron configuration? What do we have here? What does this left side always represent? 1s. So that peak height represents how many electrons? 2. All other peaks, you determine their number relative to that first one. Do we see that? This first one is representing 2 electrons. So that peak height is 2. That means this is 2s what? 2. There's 2 electrons. Then what about this one? 2, 4, 6. 3 times larger, right? 2p6. This is what? 3s2 and 3p1. It's half of 2. Do you see that? So what is that at 3p1? It is aluminum. Y'all can do this, right? Not too bad. All right. Now, just to throw a wrench in our plans, let's complicate this just a little bit. All right. I know. Now, if I'm being honest, I think this is some like 2013 AP chemistry right here. I think they said, you know what? This is too hard for those youngins. We need to stop asking questions like this. Except they are going to ask you about this. They're just not going to put it on a PES graph. They're going to ask you about exactly what we're going to be talking about in periodic trends, right? And they're what we call exception to trends when we get there. And this is, we can use PES to explain those exceptions. And if we understand it here, we'll probably understand it there. All right. So this is probably not directly assessed, but it's going to be indirectly assessed. So I'd rather go over it. All right. So, but I like this question anyway. It's a great question, I think. So as much as I remember what it says. All right. So we have 2 elements, phosphorus and sulfur. Now I want everyone to look at their periodic table. All right, if you're looking at your periodic table, you should notice phosphorus is in group 5A, right? Group 5A, and sulfur is in group what? 6A. And if we look at the nuclear charge or the effective nuclear charge, remember we talked about this the other day. Those elements in group 5A have an effective nuclear charge, ZEF, of 5. And those in group 6A have an effective nuclear charge of what? 6. And the effective nuclear charge lets us know about the relative attraction electrons have for the nucleus. Now, if we notice, sulfur has 16 protons and phosphorus has 15 protons, and they're both in energy level 3, and they're both in energy level 3p. Do you see that? Both of them. Now, what does this mean? Well, it means that if we have electrons in phosphorus, we should see, because it has fewer protons, binding energy is less at all peaks. Didn't know what we just said just a second ago? Yeah, that's what we just said just a second ago. So now let's look at let's look at these peaks on sulfur and phosphorus. Let's see if we can make some sense of this. So here we are at the 1s peak of phosphorus. We see that it's at 208, right? And on sulfur, it is at what? 239. So indeed, that 1s peak is higher for sulfur than it is at phosphorus. Isn't that what it's supposed to be? Well, it looks like everything's going well. I don't see an exception. Let's move forward. So we go to the second peak, the 2s, and we notice that this value is less than that value. The value at the 2s peak, the binding energy for phosphorus at the 2s peak is less than the binding energy of the 2s peak at sulfur. That's exactly what we expect. That's perfect. Wow, no exceptions. Let's move forward. We go to the 2p peak, 13.5, 16.5. It's still working out. Whew, this is getting exciting. Let's go to the next one. 3s, 1.95, 2.05. Mr. Schmidt, what is the problem? I don't see it. Except for when we get to this last peak, all of a sudden, the story changes. Do you see? This is a drama unfolded. Did you not feel it? So now we see that this is higher than this. Do you see that? That's weird. That should not be. Sulfur has 16 protons. Phosphorus only has 15. We would expect the binding energy at each peak of sulfur to be greater than each peak in phosphorus. But in fact, our observation is saying not so. Why is that? Why is that? Great question. Let's talk about it. All right. So there's only really one way to look at this. All right. And we're going to have to look at it in terms of our good friend orbital diagrams. You all remember orbital diagrams? We just talked about them the other day. Isn't that true? Yes. That's what I was just thinking. Thank you for thinking the same thing I'm thinking. All right. So here is sulfur, and sulfur with its 16 protons. All right. We're not going to talk about the number of neutrons. It's not important right now. And this is phosphorus with its 15 protons, right? Now we're going to draw our electrons. And we see that we have 1s, 2s, and then we see why we have to follow all of our principles and our rules, our Aufbau principle, our Pauli exclusion principle, and Hund's rule. You all remember going over those? You need to make sure you know them. So we put in the 1s, we put an up and a down arrow. Why? Because at 1s, there's 3 quantum numbers that are the same. The spin is the 4th number that is not going to be the same. You have a plus and a minus. Do you see that? An up arrow representing plus, a down arrow representing minus. So we do the same thing at the 2s. So we start at the 1s to follow Aufbau principle. We fill lower energy levels first. Then we go to the 2s. We got opposite arrows following the Pauli exclusion principle, saying that we can't have the same 4 quantum numbers. And now we get to Hund's rule, which says that when we're in degenerate orbitals, that we must fill them singly first with parallel spin. So that means up, up, up. Did they fill singly first with parallel spins? Yes. And then now they're forced to pair, down, down, down. And then we go to 3s, up and down, and then up, up, up. And what do we see there? We see a half-filled 3p orbital. Do you see that? We do the same thing for sulfur. All right, I'm just going to show this. Up, 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 down, 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 up, down, up, 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 and down. Now, what we see here is that we have 2 conditions at this 3p orbital. Here we see a condition for phosphorus in which we have 3 electrons with parallel spin, and they're each in their degenerate orbitals. Here we see one of the orbitals is filled and the other one isn't, all right? So anytime we have half-filled orbitals, that is a very stable condition, all right? So there's going to be a greater amount of attraction there, right? Just because it's a little more stable. Also, what we're seeing here, you see this first part right here. This guy right here. You see that? Notice those electrons are paired. What they're saying, this is explaining an observation. This is not me telling you how it is. This is explaining an observation. We know this occurs, and we also know that we have some kind of weird something happening by which the binding energy of that last peak is less than, in sulfur, is less than the binding energy of the last peak in phosphorus. And we didn't expect that. So now we're trying to explain this observation based off of the orbital diagram. And so what we see is there is some electron repulsion occurring right there. And I also put this in this black box here. An electron in a doubly occupied orbital is repelled by the other electron and requires less energy to remove than an electron in a half filled. So in this half filled, that's going to require more energy because there's no repulsion. It's very stable. Here, because there's two electrons right there, they're saying there's some electron repulsion, which is driving down the force of attraction or the amount of binding energy in that last peak. Do you see that? So I did spell that out for you, so make sure you look at that. So if we look at our choices on this, it says given the photoelectron spectra for phosphorus and sulfur, which of the following best explains why the 2p peak for sulfur is further to the left than the 2p peak for phosphorus, but the 3p peak for sulfur is further to the right than the 3p peak for phosphorus. So we see the 2p peak, right? Greater, less. Here, greater, less. Why? That's what they're saying. So sulfur has a greater effective nuclear charge than phosphorus. Is that true? Does sulfur have a greater effective nuclear charge than phosphorus? What was the effective nuclear charge of sulfur? 6. Where's the effective nuclear charge of phosphorus? Okay, so is that first part true? Yeah. All right, so then we can move forward. And the 3p sublevel in S has greater electron repulsions than in P. Does the 3p sublevel in S in sulfur? This is sulfur. The 3p sublevel in sulfur, does it have greater electron repulsions than what we see here? Yeah, that's exactly what we just said. All right, so do you see that? All right, and the 3p sublevel is more heavily shielded. Did we talk about shielding yet? No, we haven't. We're going to, but it has nothing to do with shielding. S has a greater number of electrons than phosphorus. So the third energy level is further from the nucleus. Does the number of electrons keeping us further away from the nucleus? 3p and 3p. Does the number of electrons change the distance? No. So that wouldn't even make sense, right? And then S has a greater number of electrons than P. So the Coulombic attraction between the electron cloud and the nucleus is greater in S than in P. You could maybe make that argument, but if you were going to make that argument, then sulfur would have higher binding energy. Do you see that? So you could make that argument, but is that consistent with what we see on this graph? And the answer to that is negatory. No, it is not. So we see that it is clearly A. Okay, then let's take a look at some easier questions here. This is what you could look like. This is what a free response question could look like on a test. All right, on your actual AB test and also on your test with me. All right, so it says on this one, how do the peak heights compare? What does this tell you about the relative number of electrons represented by each. So how do these peak heights compare? They're all the same height. So what does that tell you? They all have 2 electrons. Each peak is representing how many electrons? 2. All right, very good. Does peak height represent the amount of binding energy? No, that's where they're gonna try to catch you. They're gonna throw one big peak up here and be like, the binding energy is higher because the peak is higher, and y'all gonna be like, yeah, that's it. All right, you know why you're saying that? Because you didn't pay attention. Because did I say that ever? No. Matter of fact, I'm telling you it's wrong. So now on part B, if the peaks shown represent all the electrons in this atom, identify the element. What would be the element? So we have, what is this? 1s, 1s2, 2s2, 2p, 2. What is the element? Carbon. How easy is this? Tell me this is hard. Oh my gosh. If you have something like this on your free response, just be like, thank you for my free 4 AP Chem. All right, because this is easy. And they do have, like, this could be one whole question. Ridiculously easy. Okay, this is a really tough one. You remember core electrons? We talked about those the other day. Which peak represents the core electrons? The 1s. So could be this peak right here, right? The 1s. The 1s represents the core electrons. What do we call those two? The 2s and 2p. Valence, because they're in the highest energy level 2, right? Both of them. Wow, that was tough stuff, right? All right, we go to this next one. How many electrons are represented in each peak? How many here? On 2. How many here? 2. How do you know? They're the same height. So 2 is marked by 4 lines. So this is 8 lines. How many are here? 4. You see how it's just double? Wow, that wasn't hard. So how many electrons does the atom contain? You can add. You can get this. 8. All right. 2 plus 2 plus 4. Very good. And then how many electrons are in the valence shell? 6. Excellent. And then can you write the electron configuration for this element? 1s2, 2s2, 2p4. And what element is that? Is it nitrogen or oxygen? Oxygen. All right. Wow. You know what we did today? Today, we're able to explain the relationship between the PES of an ion and an atom, and the relationship between the ground electron configuration, and then also the interactions that occur between the electrons and the nucleus. Folks, that's all we have today. I thank you for watching. Please like and subscribe. It's wow.